Binding energy. If two or more objects are held together in some way, the binding energy is simply the energy needed to completely separate them into their constituent parts. For example, in a hydrogen atom, the electron is bound to the proton. To remove the electron requires energy, the binding energy of the electron, or the ionization energy for hydrogen. The energy needed is 13.6 electron volts, or 2.2 times 10 to the minus 18 joules. This gives a mass given from m equals E over c squared, putting in the numbers, a mass of 2.42 times 10 to the minus 35 kilograms. This is 1.46 times 10 to the minus 8 atomic mass units. So the hydrogen atom has slightly less mass than its constituent parts. The binding energy of a nucleus is the energy that would be needed to separate it into individual protons and neutrons. This will be the same as the energy that would be released if the nucleus were to be built up from individual protons and neutrons. An alpha particle has this mass in atomic mass units and is made up of 2 protons, each with this mass, and 2 neutrons with this mass. The mass defect, or lost mass in making it up, is the mass of the things it's made up of, the 2 protons and the 2 neutrons, minus the mass of what we end up with, the alpha particle. This gives a missing mass of 0.03037 atomic mass units. It's as if we've built a wall out of 50 1-kilogram bricks and found the mass of the wall to be less than 50 kilograms. To convert this mass into kilograms, we need to multiply by the mass of the atomic mass unit, 1.661 times 10 to the minus 27 kilograms, giving a mass defect of 5.04 times 10 to the minus 29 kilograms. Using E equals mc squared, we can find the energy. This comes out at 4.54 times 10 to the minus 12 joules. To convert this into electron volts, we divide by the charge on the electron, and this gives us 28.4 times 10 to the 6 electron volts, or 28.4 mega electron volts. This means that if you combine 2 protons and 2 neutrons to make an alpha particle, 28.4 MeV of energy will be released. It also means it will require 28.4 MeV of energy to split it back into the 4 separate components. What's usually more useful than knowing the binding energy is to know the binding energy per nucleon. In the case of the alpha particle, the binding energy for 4 nucleons is 28.4 MeV, so the binding energy per nucleon is simply the 28.4 MeV divided by 4, meaning 7.1 MeV per nucleon. If we plot a graph of the average binding energy per nucleon against the number of nucleons in the nucleus, we get a shape like this. These spikes refer to particular isotopes that have a particularly high binding energy per nucleon for their size of nucleus. This one is helium-4. This one, carbon-12. Right at the top here, with the highest binding energy per nucleon, is iron-56. If we head in this direction, joining smaller nuclei together to produce larger ones, heading towards iron-56, the binding energy per nucleon is increasing, and so energy will be released. Summarizing that here, we're fusing smaller nuclei into larger ones. This increases the binding energy per nucleon, and so releases energy. This is what occurs in nuclear fusion. Heading in this direction, splitting larger nuclei into smaller ones, again approaching iron-56, also increases the binding energy per nucleon and will release energy. I've summarised that here. So we're splitting larger nuclei into smaller ones. This increases the binding energy per nucleon, and so releases energy. This is what occurs in nuclear fission. We've already looked at the alpha particle forming and releasing energy. This is an example of nuclear fusion. Now we'll look at the energy released when a uranium-236 nucleus undergoes fission to become lanthanum-146, bromine-87, and 3 neutrons. So I've shown that here. The uranium-236 becomes lanthanum-146, bromine-87, and 3 neutrons. Here we've got the binding energy per nucleon for uranium-236, lanthanum-146, and bromine-87. So the binding energy after fission is equal to 146 nucleons multiplied by the binding energy of lanthanum plus 87 nucleons multiplied by the binding energy of bromine, giving a binding energy after fission of 1975.19 MeV. The binding energy before fission is equal to 236 nucleons multiplied by the binding energy of uranium-236, giving 1791.24 MeV. So the increase in binding energy is the binding energy we finish with minus the binding energy we started with, an increase of 183.95 MeV. This means that the energy released by this fission of uranium-236 would be 183.95 MeV.